All right, in our last installment of the gas chapter, we have before and after problems. This is what we would call the combined gas equation. And it's essentially what happens when you take PV equals nRT, the ideal gas equation, and you divide by NT on both sides. N's and T's cancel, and this equals R. So if R is the magic number for all gases, that means the gas before versus the gas after will have R in common. So in these problems, you potentially have 7 variables and you're missing number 8, and then you're solving for number 8. The reality of introchem is we rarely use moles in combined gas law equations ever. We just assume that there's the same number before and after. So typically what you're going to see is 6, and they're going to give you 5. You solve for the one that's missing. So again, N's pretty rare. I don't think of any examples in the homework of the exam that you actually see that. There is one of these on the final exam. The 3 that remain for the 5 that are on there are based on STP calculations we'll do at the end. So there's lots of variations of the combined gas equation. You can solve for P's, you can solve for T's, you can solve for V's. Notice in all situations what you're seeing in common is T's cancel, V's cancel. P's cancel, V's cancel. T's cancel, V's cancel. P's cancel, V's cancel. T's cancel, P's cancel. P's cancel, T's cancel. So always the unit that you have is the unit left over. Unit you have, 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 unit left over. Notice everybody else cancels. And that's why this shows up at the end of the semester, because there's so much other unit cancellation going on. In order to get any of these, you would start out at P1, V1, N1, T1, P2, V2, N2, T2. That's where we start. And then what you'll notice is we cross multiply. We get P1, V1, N2, T2. We get N1, T1, P2, V2. Then pick one. Once you pick one, you're going to divide by everybody else. So notice what we see with P1. If we want P1, then we divide by everything else. So V1, N2, T2. Over here will be V1, N2, T2. And notice, since we don't use N very often at all, these cancel, cancel, cancel. This minus the N's is exactly what they have here. So by cross multiplying and dividing, you can find any of these from the original equation that I give you on the final exam. But again, this is only one problem on the final exam. So not crucial that you can survive it, but it'll definitely give you 2.5 points if you do. In these kinds of problems, I like to have a double chart. So this is kind of set up in that double chart kind of mode. This is our before, and over here is our after. And notice that V, so the container, the volume of the container doesn't change. So this is irrelevant because it stays the same. The number of molecules, because we haven't opened the tank or added to the tank, hasn't changed. And this is pretty common to see, even though we have 8 possible variables, a lot of them are held constant to make the problems a little bit simpler. So we can really, in this situation, ignore that any of this exists at all. So if we have P1, V1 over N1, T1 to start, that's equal to P2, V2, N2, and T2. And what we just showed you is that volume and moles are gone, so we can scribble this one out, scribble this one out. Volume didn't change, number of molecules didn't change, and we're left with P1 over T1 equals P2 over T2. We can do what we just did. We can cross multiply. We get P1 T2 equals P2 T1. So it's taking this one times this one, and then this one times this one. Once we realize that we're looking for P final, which is really just P2, we can divide by T1 on both sides. These will cancel. So out of all that algebra work and all that effort, this is our equation that we're working with right here. So based on that equation, we have P1 T2 over T1. So we're going to take P1 from our chart, put that on top. T2 from our chart over here, put that on top. And then T1, put that on the bottom. So here they solve for us. Notice these are just 1s and 2s, i's and f's, i's a 1, f's a 2. Notice our Kelvin cancels, and we get 10. We could have used kids in the playground to figure that out, though, because if you realize that temperature doubles, went from 200 to 400, then we'd expect pressure to double because they're proportional. So we didn't really need our calculator to prove that, but we could if we wanted. So you'll see problems where they talk about what happens when pressure doubles, when things are cut in half. If you want to do math on problems that say double, just use 1 versus 2. That's the easiest way to double without using any units. If it says quadruple, use 1 and then versus 4. So in your chart of pressures, if they say, if they give you a problem where it's P's, V's, and T's, which are the most common, before and after. If they say, what happens when pressure doubles, say 1 and 2. What happens when volume is cut in half, then say 2 and 1. What happens to temperature, then you just say 1 and a question mark, and then you solve that way. So you can use generic numbers for doubling and tripling or quadrupling or cutting in half by plugging them into that. If you can't do the kids in the playground analogy in your head, do the math in your calculator instead. Last idea in this chapter is based on STP. STP is not a motor oil, it's a standard temperature and pressure. Standard temperature is 0. When we convert it to Kelvin by adding 273, we get 273, and the standard pressure is 1 atmosphere. What's nice about STP is if a problem mentions it, and they have to, we can use the magic number per 1 mole as a conversion. So if we have 1 mole, we have R. We have standard temperature. If we have standard pressure, then we get this magic number. And if we have this magic number, it's just one more conversion, like 1 mole equals Avogadro's number, like 1 mole is grams on the periodic table, like capital M is moles per 1,000 milliliters, like subscripts, like coefficients. If they say STP, we can use this magic number every single time. So let's show you a couple examples, and then we're just about done with this chapter and with this semester. So this gives us our last piece of the puzzle that we mentioned now 3 weeks ago. We have periodic table mass equals 1 mole, we have Avogadro's number equals 1 mole, and we have molar volume, which is the magic number 22.4. That's the one that we're going to find in experiment 24. So what volume is occupied by 10.5 grams of helium? This is very similar to a final exam question. So again, we have one number. So anytime you have one number, you put it out front. 10.5 grams of helium. Next thing we're going to do is get rid of grams. Go figure. Something we've done for now 4 weeks in a row. We can get 1 mole, and then we can use the periodic table. That's just going to be helium. Helium weighs about 4 grams. Grams of helium cancel. We're going to have to cancel moles of helium, so set up another conversion. Moles of helium. They said STP, check, so that means use the magic number 22.4 liters for any gas at STP. So that's how fast these problems should be. They should just be adding this, conversion of 22.4 liters. In this case, right side up, because we want moles to cancel, but you could just as easily take liters and get rid of it by flipping it over. So there's a problem like this on the final, where you take grams and you convert it to liters using 22.4. What is the density at STP? Well, that one's a little bit easier than the density I showed you a moment ago, because density at STP, I gave you this on the final exam as well. Density is molar mass over molar volume at STP. Molar mass comes from the periodic table, that's in grams per mole. Molar volume is the magic number, 22.4 liters per mole. So if you cover up D, you get molar mass over molar volume. The molar mass of helium is straight off the periodic table, 4 grams per mole. Molar volume is the magic number, 22.4 liters per mole. Moles cancel, and we get grams per liter left over, and there's one of those on the final exam. The last problem on the final exam is going to be a stoichiometry problem using 22.4 liters, but it has a balanced chemical equation where you use 22.4 liters in first and third, just like our other chapters. So I didn't show you one of those, but there is some of those in the lab book, and there will be some on the study guide as well. So in this chapter, we really have 3 kinds of problems. We have what I would call a method 1 problem, where we have one variable of each, and then we use R. And as long as our units cancel with R, we should be fine. So when you're using pressure, make sure it's in atmospheres. If it's not, you have to convert it. If you're using volume, make sure it's in liters. If it's not, you're going to have to convert it. If you're in grams, find moles from the periodic table. And if you're in Celsius, make sure you convert to Kelvin. As long as those units match R, you should be fine. Then you can use the equation, pick which one's missing, and then divide by the others. Make sure you do it on both sides, and then you should be able to plug them in your calculator pretty quickly afterwards. If you're not sure about method 1 versus method 2, well, method 2 is going to have more than one value. So what I mean by that is, if you're in a method 2 kind of problem, expect to see an atmosphere in the problem. So anytime you have 2, that means you can't use the ideal gas equation because it can only fit one variable for pressure. So look for maybe 2 liters. Rarely will you ever see moles, but if there were 2 moles, you could guess that would probably be a before and after kind of problem. And then look for temperature. If you see 2 Celsius, you're going to have to convert to Kelvin. But if you see 2 Kelvin, that's even better because then you don't have to convert. But anytime you see 2 units in the same problem of the same type, you know it's a method 2 kind of problem. The easiest one to recognize is method 3 because it's going to say STP somewhere. If it says STP somewhere, it's telling you that it's safe to use the 22.4 magic number. If STP is not mentioned, then you can't use that number. Standard temperature is 0 degrees Celsius or 273 Kelvin. Pressure is 1 atmosphere, which is also 760 millimeters of mercury. So if you change pressure, you're going to change temperatures, you're going to change everything. If you change temperature, you're going to change pressure as a result. So because these two are intertwined, as one goes up, the other goes up, as one goes down, the other goes down, it's only these numbers that can work. If you change these numbers, so if it's not equal to those numbers, then you're going to have to use PV equals nRT, because that's an equation that can deal with changes in pressure, changes in temperature. But if you're at 0, if you're at 1 atmosphere, it's safe to use this number. And you can plug it in just like any kind of unit conversion. So, try to hold back the tears. Intro Chem is over. And now it's time to get ready for the final exam. Hope you've enjoyed the show. See ya.